Hello, my name is Dr. Hammad Haider and you are watching sqadia.com. Today, my lecture would include embryonic period, that is, the period from third week onwards till eighth week. My lecture would include neurulation and neural tube defects. That how I've already discussed in the previous lecture that how the two germ layers are formed, that how the cells divide to form an epiblast and hypoblast, and then they further divide into three germ layer or trilaminar disc formation, which is ectoderm, mesoderm, and endoderm, and how these cells further divide to form the different parts of the embryo will be discussed in today's lecture. So we will be discussing neurulation and neural tube defects, formation of neural crest cells and their derivatives, and how this migration of neural crest cells occurs to form different structures in adults, derivatives of ectoderm, and what are the cells which initially form ectoderm and then how they migrate and how they arrange themselves, which on later on lead to different structures in the adult. Derivatives of mesoderm. We'll be discussing all the three parts of the mesoderm, that is the paraxial mesoderm, intermediate mesoderm, and lateral plate mesoderm, and how paraxial mesoderm leads to different structures, intermediate leads to different structures, and lateral plate mesoderm form two different layers, which is the parietal mesoderm and visceral mesoderm. We'll be all discussing in this lecture. Then the third layer, as I already told you, it is actually the three layers: ectoderm, mesoderm, and endoderm. We'll also be discussing the derivatives of mesoderm. What are the structures in adults which are derived from endoderms? And then the folding of the embryo. Actual embryo, how it folds into the normal fetal position, because after 8 weeks, the fetal period has to start, and how this embryo folds to arrange it in a position so in which the normal fetus is seen on an ultrasound. So what is embryonic period? Embryonic period or period of organogenesis occurs from third to eighth week of development. Why it is called organogenesis? Because all the organs are actually formed during this week. This is the time when each of the three germ layers, which I've already discussed in the previous lectures, the formation of ectoderm and mesoderm and endoderm. These are the three germ layers: ectoderm, mesoderm, and endoderm give rise to a number of specific tissues and organs. So before we start, we already discussed this, that we'll be discussing neurulation. So what is neurulation? It's actually formation of neural tube from a notochord. This whole process is termed as neurulation. So how it all starts? It starts at the beginning of the third week of development. At the exactly third week, the ectodermal germ layer has shape of a disc that is broad in cephalic than in the caudal region. I've already discussed this in the previous lecture, that actually initially it's like two the bilaminar discs. There are two layers, epiblast and hypoblast. They are sandwiched together. Gradually epiblast starts to divide, and then eventually this leads to formation of three trigeminal discs. There's an ectoderm on the top, there is mesoderm, and then there's endoderm. Endoderm is forming the roof of the yolk sac, while ectoderm is aligned with the amniotic cavity. So by this time, if you see it in the 3D, it's actually an elongated oval-shaped coin, in which the cephalic end, which is mainly the head region, is actually more broad, while the caudal end, which is the limb region, it is slightly narrowed. So this is an oval-shaped elongated coin, which is at this time, at third week of development. So notochord and precaudal mesoderm induces the overlying ectoderm to thicken and form a neural plate. Formation of neural plate from the notochord is termed as neurulation. And cells of the plate make up a neuroectoderm, and the induction represents the initial event in the neurulation process. How this process is actually exactly occurs, although this is still unclear. There have been certain genes which are involved in this process. They release certain factors such as fibroblast growth factor, and there is also inhibition of tissue growth factor beta. There is release of cordin, noggin, and phosphatin. there's different kind of chemicals which are being released, but exactly how genes cause the release of certain chemicals and they induce this mesodermal tissue to induct, further cause a division of the cells in the ectoderm and notochord and prenotochordal plate. So this is still very much unclear. So what we know up till now is that the notochord and precaudal mesoderm induces the overlying ectoderm to thick and form a neural plate. So this is what I was talking about. If you see this diagram, this is like an oval shape or elongated coin, which is more broad at the cephalic end, which is the head end, while this is the caudal end. If you see it this on this is the AP view that you are seeing it from the top. If you are seeing it from this cavity, amniotic cavity would be on the top, and you can see your yolk sac or your secondary yolk sac at the bottom. Now this is showing it the lateral edge. This is a bit of oblique view. This is, I was talking, you can see an elongated coin which is more broad at the cephalic end, and then this is the yolk sac, and then this is the amniotic cavity which is, you can see through it, and there is a formation of primitive node and then a primitive streak. What actually happens is that in between, after this induction has occurred, these cells form a primitive node. This primitive node has actually formed as, for example, if this is the layer of the ectoderm, and certain cells starts to proliferate from here and here as well. Gradually they become like this. Eventually there will be a groove formation, not because the reason that cells are actually dipping in, but rather the cells are dividing on the sides and growing out. So when after some time when cells are divided, those cells who are forming the ridge of that growth are actually lying higher than those cells of the plate. So they look and appear like a groove formation. So this is the first thing which starts to appear, which is a primitive node. The cells here starts to divide actively and form a structure termed as primitive node. From here onwards, this primitive streak will be formed, and gradually the cells will continue to divide and arrange themselves in such a way that on one end there is a primitive, this is a ridge-like formation takes place, and inside it appears to be like a groove-like structure. So this is what I was talking about. There's a molecular regulation. Although these mechanisms are being understood and there's still a lot of research going on, but exact mechanism is still unknown, although it is speculated that yes, there is an upregulation of fibroblast growth factor, and tissue growth factor beta is actually downregulated. That is, there are certain genes which are expressed which increase the formation of FGF beta, while TGF beta is actually, the production of TGF beta is reduced. Then there is secretion of certain molecules such as cordin, noggin, and folastatin. I have already told you. Now there are certain genes which present in these cells which cause the release of these molecules, but exactly what are the receptor mechanism, what is the signaling pathways, we are still not clear. Inducers of hindbrain are mainly WNT3A gene and FGF and retinoic acid. So what is neurulation? Is the process whereby a neural plate is formed from the neural tube. We knew it, there was a notochord form a neural plate will further form the neural tube. This whole process is called as neurulation. Initially, if you see a structure, it was a flat structure. It was kind of a flat elongated coin with cephalic head which is more enlarged. Then gradually cells started to divide. They became arranged such a way that a groove started to appear. This is termed as neural groove, and once this continues, eventually they align and join to form a whole tube-like structure. This becomes a neural tube. So by the end of the third week, the lateral edges of the neural plate become elevated to form neural folds, and depressed mid-region forms the neural groove. Now if you see over here, now this is the point. You can see this is a primitive node, a primitive streak formation took place. The migrations of the cells actually go from caudal to cephalic end. So mainly the growth is initially towards the cephalic end, and as they're growing, and this the lateral edges actually rise above the medial side, and this forms the neural folds, and in between a groove starts to appear, which is termed as the neural groove. Now gradually this neural groove will eventually, the two lateral edges will come together to form a neural tube. So fusion begins in the cervical region, fifth somite level, and proceeds cranially and caudally. So if we have to understand this as a tube structure, it starts to join not at one end. That is, it's gonna be new formation, neural groove will take place, and then suddenly abruptly it's gonna time. Rather, this joining of the tube starts at the midway, actually at the fifth somite level, which is for in adults it's at the cervical level. Now this is the point it starts to unite first, then it also progresses cranially, that is going more towards the cranial region, as well as to caudally. So actually it starts in the middle and progresses more cranially as well as caudally. As a result, the neural tube is formed. Until fusion is complete, the cephalic and caudal ends of the neural tube communicate with the amniotic cavity by way of anterior and posterior neuropores respectively. So I told you, if you see it in a 3D, this was the neural plate. Amniotic cavity was lying on the top. Then this was the mesoderm. Then this was the endoderm, and then there is a yolk sac underneath. So if you see it in a 3D, now this ectoderm started to divide to form initially a neural groove. Then first neural ridges appeared, then neural groove formed, and eventually neural plate. But this is where the amniotic cavity is. So it has to communicate at anterior and posterior neuropore with the amniotic cavity. And this is the diagram which is exactly showing that at this level it has started to unite and to form a neural tube. From here onwards it progresses more cranially as well as caudally, and gradually closes and closes to form a tube like this. Once the whole tube has been formed, still there is opening, anterior neuropore is there and posterior neuropore is there. And this is important because if this communication remains open, there are different clinical entities which appear if anterior posterior neuropore is. So they usually close at different dates, and if they do not close, this leads to an abnormality. Closure of the cranial neuropores occur at approximately 25, whereas anteriorly closes at day 25, which is at approximately roughly 18 to 20 somite stage. I will be discussing what is the somite stage later on in upcoming slides. Whereas posterior neuropore closes at day 28, which is 25 somite stage. And neurulation is then complete. Central nervous system is represented by a closed tubular structure with a narrow caudal portion and spinal cord, and with more broader cephalic portion characterized by number of dilatation and brain vesicles. So mainly the brain, the cerebellum, the spinal cord, and all this will be formed by this neurulation. In adults, this is represented by this structure. If there is an abnormality in the posterior neuropore or anterior neuropore, different things, different clinical entities appear. For example, if there is no anterior neuropore or anterior neuropore fails to close and cavity, there is definite link or communication between amniotic cavity and neural tube, then this results in anencephaly, that the brain vesicles do not appear and the brain of the baby does not develops. As a result, this leads to a disaster condition called as anencephaly, in which the baby is born but there is no brain. So that babies usually do not survive beyond more than 30 to 1 hour after the birth. Usually they die, as brain is main organ which is controlling every other organ. So that is not practically possible for a baby to survive without a brain. And if posterior neuropore is kept open, or for some, then another pathology which is termed as spina bifida or meningomyelocele, I will be discussing later on. So this is the diagram which is showing embryo at the end of the neurulation. Now this is just at the 25 days when his anterior neuropore is about to close. Now can you appreciate, this is if you're seeing this embryo laterally, and it's like this, if it's lying like this and you're seeing it like this. So this is the cranial end, this is the caudal end, this is the communication with the yolk sac, and then as you can appreciate, this is the neural tube formation which has actually taken place. By this time, first and second pharyngeal arches have started to appear, and I will be discussing how the endoderm actually derivatives occur later on. And this is the communication, and this is the posterior communication via posterior neuropore. And amniotic cavity lies around right over here. At 28 days, anterior closes at 25th day, and at 28 days you can appreciate the posterior neuropore has closed. Now this is a complete tube-like structure which is going on. Like this will result in the formation of later on brain vesicles will be formed. This will form the cerebellum, and certain spinal cord will also be formed. In adults, all this nervous tissue, that is the brain, the forebrain, midbrain, hindbrain, cerebellum, spinal cord, this is all, this mainly is given rise by these structure. Now we will be coming to another entity, is the formation of neural crest cells. In adults, you have ever wondered, okay, this is a tube has formed, there is a spinal cord in it, but from where does this nervous tissue which is present in the medulla, adrenal medulla, has come? You have ever wondered from where these ganglia, which are actually not lying inside the vertebral canal, from where they have come? There must have been certain cells which would have migrated away from this axis to lodge somewhere else and form the formation of these ganglia and spinal nerves and this adrenal medulla. Then there comes the neural crest cells. These are the cells actually. Now if you see this diagram, this is representing the time when the neural groove formation has taken place. As you can see, the neural ridge is there. Its cells are dividing and elevating themselves over a certain level, over here and over here, and in between there is a neural groove. Now this cells of this neural ridge starts to migrate and form the neural crest cells. These migratory cells, why they are called neural crest cells? Because these migrate to other areas to form a nervous tissue there. As the neural folds elevate and fuse, cells at the lateral border of the crest of the neuroectoderm begin to dissociate from their neighbors. The cell population of the neural crest will undergo an epithelial to mesenchymal transition as it leaves the neuroectoderm by active migration and displacement to enter the underlying mesoderm. So what happens is, here the neural tube is closed but cells are continuously dividing. And this is the mesoderm, is a paraxial intermediate lateral plate, and this is the endoderm. If you see in this diagram, this is showing the migration from this is a cell which was present right over here. They started to migrate like this. Here they form dorsal root ganglion, then they further migrate to form sympathetic and parasympathetic ganglion. They also migrate, as we know, the endoderm will form the lining of endothelial lining of the gut, but there is mesenteric and orphic plexus which is present. That plexus, how this nerve tissue is actually formed, is formed from this migratory of these neurocrest cells. These cells migrate around the endodermal tissues and form the enteric ganglia. Similarly, they also migrate towards the renal suprarenal gland area, which is actually this nephrogenic area, and renal and adrenal glands are actually formed by the intermediate mesoderm. They migrate and form the nervous tissue in the adrenal medulla in the adult. So adrenal medulla, the nervous tissue of the adrenal medulla in the adult is derived from the neurocrest cells. So this is the list of a long list of derivatives, the neurocrest cells. As they migrate in different structures, they form a nervous tissue in different areas of the body. So they form connective tissue and bones of the face and skull. They form cranial nerve ganglia. They form C cells of the thyroid gland, conotruncal septum of the heart, odontoblasts, dermis in the face and neck, spinal or dorsal root ganglia, sympathetic chain and pre-aortic ganglia, parasympathetic ganglia of the GIT, adrenal medulla, Schwann cells, glial cells, meninges, melanocytes, smooth muscle cells to the blood vessel of face and forebrain. So these are all the derivatives of neural crest cells and derivative of neuroectoderm. So ectoderm is actually giving rise to neuroectoderm, and they are further giving rise to formation of spinal cord, brain, and all these vesicle formations. And then there are neural crest cells which are giving rise to all these structures. So up till now we are mainly covering and concerned with the derivatives of the ectoderm here. This is what I was talking about. If anterior neuropore remains open and the cavity communicates with the amniotic cavity, this results in an encephaly. That in this photograph you can appreciate the child does not have any brain, and a child cannot survive without a brain. In this formation of no brain is termed an encephaly. While if posterior neuropore leads to spina bifida or meningomyelocele, 400 micrograms of per day folic acid. Now this neural tube formation is highly needs a lot of folic acid. If at this time, at 3rd to 8th week, mother does not take enough folic acid, this results into neural tube defects. Neural tube defects include encephaly and spina bifida. So this folic acid is paramount of importance for the closure of anterior and posterior neuropore. Coming to the derivatives of ectoderm. Ectoderm germ layer give rise to the organs and structures that maintain contact with the outside world. As I have already showed you that ectoderm form the neuroectoderm, which mainly give rise to the nervous tissue. This neuroectoderm, there were certain cells which formed the neural crest cells. They migrated to form the peripheral nervous system in the mainly in the body, and this is just a small sort of a summary of what are the derivatives. All the derivatives of neural crest cells are also actually derivatives of ectoderm. For example, central nervous system, peripheral nervous system, sensory epithelium of ear, nose, and eye and skin, including hair and nails, pituitary, mammary, and sweat glands, and enamel of the teeth. The odontoblast, which have migrated and formation took place from the neural crest cells, eventually lead to enamel of the teeth. So what have we covered up till now? Neurulation and neural tube defects, formation of neural crest cells and their derivatives. We have covered up till now that the derivatives of ectoderm. As I told you that others, there were 3 layers: the ectoderm, the mesoderm, and endoderm. And mesoderm further has 3 parts: paraxial, intermediate, and lateral plate. Lateral plate mesoderm is further divided into 2 in forms the visceral and parietal mesoderm. And how all these outlines to form different structures I will be discussing in next slides. So coming to the derivatives of the mesoderm. Initially, mesodermal cells form loosely woven tissue on each side of the midline. Actually, axis is where the neural tube has formed. Neural tube is the center here, and this is the axis of the fetus at this moment. Anything around lying along this axis or parallel will form the paraxial part. So if you see this diagram, this is the axis. This is the neural groove formation is taking place. By the time though this neural groove is taking place and neural tube is not completely fused, the mesoderm along with adjacent to this neural groove, which is gonna be later forming the neural tube, is termed as the paraxial mesoderm. And just away from this is formed the lateral plate. There is a mesoderm which connects this paraxial and lateral plate mesoderm is termed as intermediate mesoderm. As the cell starts to grow, you can appreciate almost the neural tube has formed. By this time the neural crest cells would have started migrating and neural tube is about to close. This is the part which is forming the paraxial mesoderm. Then this is the lateral plate, so it is unfolding in, and this is the intermediate mesoderm. As you can very clearly appreciate later on over here that this is paraxial. Now the neural tube is completely closed. Paraxial mesoderm here, this is intermediate mesoderm, and this is lateral plate. And if it is it is dividing into 2 layers, that it is surrounding the amniotic cavity. This is the amniotic cavity. Surrounding the amniotic cavity, this is termed as parietal mesoderm. Now this is the endoderm, and this is the yolk sac, and the mesoderm which is surrounding the yolk sac is termed as the visceral mesoderm. And this diagram is actually also showing the folding of the embryo. I will be discussing how this embryo actually folds as well on its layer. So later on, definitive structures are actually formed. By the 17th day, they proliferate to form a thickened plate around the midline, termed as the paraxial mesoderm. More laterally, mesoderm remains thin and termed as the lateral plate mesoderm. There is intermediate mesoderm which connects the paraxial and lateral plate mesoderm, which I just told you. So how this lateral plate mesoderm is divided, I've already discussed a bit. That lateral plate mesoderms further divides into two layers. There is parietal layer and visceral layer. Always remember, viscera means organs. The layer surrounding the organs would be visceral layer, and other than that would be parietal layer. In this, one has to remember that endoderm is forming the roof of the yolk sac. Endoderm will give rise to mainly the endothelial layers of the major organs. If you see it over here, now this is the amniotic cavity, and the layer surrounding this amniotic cavity is the parietal mesoderm, as you can write, it is written over here. This is the endoderm, this is the yolk sac, and roof of the yolk sac is formed with endoderm. Here this layer, which is called as visceral mesoderm, is which surrounds the yolk sac here. This is the layer which of the mesoderm which surrounds actually the yolk sac is termed as visceral mesoderm. As you can see it, appreciate more clearly over here. It's almost the same diagram, but trying to again convince it how its folding of embryo actually occurs and how this layer gets separated. So what are the derivatives of the paraxial? Where was it? It was just adjacent to the axis or mainly the neural tube. Mesoderm lying just adjacent to the neural tube is termed as the paraxial mesoderm. So it starts to organize into segments by beginning of the third week. These segments are known as somatomeres. Each segment of this paraxial mesoderm is known as somatomeres. Each somatomere exists as a concentric whorl of mesodermal cells around a center of unit. They appear like a donut-shaped cells. So if you have to understand it, paraxial, this will be the neural tube, and there will be donuts shapes, circular structures around this neural tube. These are from the paraxial mesoderm. There are 4 occipital, 8 cervical, 12 thoracic, 5 lumbar, 5 sacral, and 8 to 10 coccygeal pairs. So there is a huge number of them. Initially, the first occipital and last 5 to 7 coccygeal somites later on disappear, while remaining somites form the axial skeleton. Now, as we already formation of spinal cord has taken place, but what about the vertebral column? Now, this vertebral column arises from the mesoderm, and how it arises, I will be just discussing. How this paraxial mesoderm differentiates into different structures. So how this molecular regulation of somite formation is taken place? Formation of segmental somites from unsegmented pre-somatic paraxial mesoderm is dependent upon segmentation clock established by cyclic expression of number of genes. There is a notch gene or notch WNT gene signaling pathway is involved in the formation of somite. And there is cyclical increase in notch proteins to induce differentiation of somites and then decrease signals in differentiation of next somite. So what actually happens is that paraxial mesoderm, if you are supposing this is the neural tube, there is one paraxial mesoderm here, there is here, and there is here, and then there is here. Now there will further first increase the notch proteins, and this part will differentiate to one somite, then they will decrease, and as a result this part will differentiate to another somite. And that's how the whole all along the neural tube the somite differentiation takes place. We can at this stage count the number of somites which can be present, and there is a clinically important correlation here that there is with a certain age and days different number of somites is present, and if on ultrasound these number of somites can be counted, and this actually signifies the exact age of the embryo. For example, this is the table which is showing exactly the number of somites present at different age. If at 20 there are almost 1 to 4, at 21 they become 4 to 7, 22 they become 7 to 10, and that's how at 30 they become 34 to 35. But not all 35 remain. As I've already told you, the first occipital and lateral 5 to 7 coccygeal would disappear. So almost 7 to 8 somites later on disappear. So at the end, it's almost 20 to 20 somites which remain. These cells then undergo a process of epithelialization and arrange themselves in a donut shape around a small lumen. By the beginning of the 4th week, cells in the ventral and medial walls of the somite lose their epithelial characteristics and become mesenchymal again, and shift their position to surround the neural tube and notochord. Collectively, these cells form sclerotome that will differentiate into vertebra and ribs. Cells of the dorsomedial and ventrolateral edges of the upper regions of the somite precursors the muscle cells, which while cells between these two groups form a dermatome. Now one has to understand, as I've told you, that this is a donut-shaped structure. There is a medial wall and there is a dorsolateral and ventrolateral edges. Now, dorsolateral ventrolateral edges give rise to dermatome or a myotome. These are the cells which are dividing to actually increase in number and will give rise to the muscles and skin over this area, while sclerotome will form the cartilage and the bony part of this. So as I've told you that we discussed the spinal cord formation, but vertebral formation now will occur from this sclerotome. That cartilage and the bony and osseous part would be from this sclerotome formation. Now this is the diagram again coming to the neural group. This is the central axis. This is the notochord. This is the donut shaped structure, which is the paraxial mesoderm. As you can see, this is the ventromedial wall. This is the dorsolateral and ventrolateral wall of the somite. Now this wall will give rise to dermatomyotome, while this will reach to sclerotome. And sclerotome will form the cartilage and bony and osseous parts, while dermatomyotome will form the dermatome and myotome of this type at this level. Hence, each somite forms its own sclerotome, the tendon, cartilage, and the bone component, while its own myotome providing segmental muscle component and its own dermatome which form the dermis of the back. That's why if you see how the spinal nerves are arranged in the adults, that when these neural crest cells which actually have traveled along this is how it happens, that the neural crest cells have traveled and this paraxial mesoderm differentiates to form a sclerotome which goes along, as well as a dermatomyotome which goes as well. So at L1 vertebra, if you see in adults, the vertebral osseous or bony part is actually derived from mesoderm, but spinal cord going in between is actually derived from the ectoderm, and the spinal nerve which is coming out going into the dorsal root ganglia is derived from the neural crest cells. This is also a diagram which is showing somite differentiation, and this is actually an advanced time, an advanced stage. This is, you can appreciate, there's a dermatome. This is a myotome which is formed on the ventrolateral edges, while the sclerotome which will form the bony, tendon and osseous component is at this level. Now this is actually differentiated, and then it differentiates into this diagram. Coming to the derivative of intermediate mesoderm. Now paraxial mesoderm, we know that it's going to form the sclerotome which will form mainly the bony component, the cartilage and the tendon. It will form the myotome and form the dermatome. So what are the derivatives of intermediate mesoderm? Intermediate, I've discussed this in the previous lectures, that it was the allantois which was giving rise to the excretory organs, for example kidneys and nephrogenic ducts. But in humans, it is the intermediate mesoderm which gives rise to excretory organs. Intermediate mesoderm which temporarily connects the paraxial and with the mesoderm with the lateral plate mesoderm differentiates into urogenital structures. In cervical and upper thoracic region, it forms the segmental cell clusters called as the future nephrotomes, whereas more caudally it forms an unsegmental mass of a tissue, the nephrogenic cord. Excretory units of the urinary system and gonads develop from the partly segmented intermediate mesoderm. As I've already discussed, now we are left with third part of the mesoderm, which is the lateral plate mesoderm. Mesoderm from the parietal layer together with the overlying ectoderm form the lateral body walls. Now we have to understand what was the parietal mesoderm came from. It was that layer of mesoderm which was surrounding an amniotic cavity. And amniotic cavity was there is an ectoderm and this parietal mesoderm. They combine to form a lateral body folds which lie in the adults. But there was the parietal layer of the lateral plate mesoderm then forms the dermis of the skin in the body wall and limbs, the bones and the connective tissue of the limbs and the sternum. While mesodermal cells of the visceral layer form the thin serous membrane, why the visceral layer is the one which is actually surrounding the yolk sac, and yolk sac is actually surrounded by the endoderm. When endoderm form the endothelium of the gut and everything, they surround this to form peritoneum. When it comes and this endoderm forms the heart, this visceral mesoderm forms a thin layer of pericardium around this heart. When this endoderm forms the pleura, there is a small thin layer of cells of this visceral mesoderm which form the pleural cavity. Coming to the derivatives of endoderm, we are left with one thing now. The gastrointestinal tract is the main organ system derived from endodermal germ layer. The tube is divided into three regions: the foregut, midgut, and the hindgut. And how the differentiation takes place, we will be discussing in different lectures. But one has to understand that if we see this diagram here, now this is the neural plate. This is how the neural groove has started to appear. Now this is, if you're watching it from the side, this is the amniotic cavity. Mesoderm surrounding the amniotic cavity forms the parietal mesoderm, and this along with this ectoderm around over here will form the lateral body wall folds. This mesoderm here at this is surrounding the yolk sac, and this is the endoderm which is also present, and you can see which is forming the roof of the yolk sac as well. Now this will fold. Now as the embryo will enlarge and start to fold in, now this will form a tube-like structure eventually, this endoderm will be lining the endothelium of the gut mainly, and around that a layer will be surrounding it, is called as the peritoneum, which will be formed by the visceral mesoderm. So we have to understand that in adults there is an opening which is called as oral cavity. You eat and it goes into the gut. Although pharynx is not technically a part of the oral cavity and is not derived from endoderm. Similarly, anal canal is not all of it is derived from endoderm. So there at a time that this point, and when you're at the cephalic end, there is an ectodermal endodermal membrane which is called as oropharyngeal membrane. Now this, once this ruptures, this is the point which in adults is actually formation of oropharynx. That there's an oral cavity, behind that is the oropharynx, and then it actually goes into the laryngopharynx. So this oropharynx is that part which is actually ectodermal endodermal membrane, which later on ruptures to form the cavity between the gut, which is the endoderm mainly, and the pharynx, which is derived from the ectoderm. Similarly, cloacal membrane. In the fourth week, the oropharyngeal membrane also ruptures, establishing an opening between the oral cavity and a primitive gut. And anus and cloacal membrane in the hindgut also terminates temporarily at endodermal ectodermal membrane, the cloacal membrane. This membrane separates the upper part of the anal canal, which is derived from endoderm, from the lower part which is derived from proctoderm, which is further derivative of ectoderm, which is formed by invaginating pit lined by ectoderm. In adults, if you see, there is a clear-cut transition in, if we are studying the histology of the lower gut and the rectum, we appreciate that there is clear-cut different epithelium, then there is a abrupt discontinuation and endothelium starts. The endothelium is derived from endoderm, while squamous epithelium, which is lying outside, is actually the derivatives of ectoderm. And it's due to this reason that the cloacal membrane is actually ectodermal endodermal junction. And this membrane, once ruptures to starts and create an opening which remains permanent opening as an anal canal. So what we have derived from the endoderm, during further development, endoderm give rise to epithelial lining. Up till now, we know that it is the gut mainly, epithelial lining of the respiratory tract, parenchyma of the thyroid, parathyroid, liver, and pancreas, reticular stroma of tonsils and thymus, epithelial lining of urinary bladder and urethra, epithelial lining of tympanic cavity and auditory tube. In a way, it's very simple to understand. All those structures which are connected, which make our connection to the outside world, are mainly derivatives of ectoderm. All those connections which are mainly surrounding our organs are mainly derivatives of endoderm, and then in between there's actually mesoderm, are certain structures which are somewhat in the middle. So this is a diagram which is showing the endoderm derivatives. Mainly it is the gut. Mainly it is the pharyngeal gut, which is actually from the oropharynx. And this is lung bud appearing when all the parenchyma of the lung will be formed. All the endothelium and parenchyma of the stomach, foregut, midgut, and hindgut, and cloacal membrane, which will once rupture to form the ectodermal endodermal junction. We discussed this all, but one has to remember that it is occurring at third to eighth week of pregnancy. Not all mothers usually have a regular menstrual cycle. We discussed in the previous lecture that average time is from 22 days to 33 days, but not all have this kind of menstrual cycle. This can go on. There some females have a menstrual cycle of almost 2 months, 3 months as well, and it's at this point it's not very easy to differentiate that okay, a female is pregnant or there is only delay of menses for some other reason. So what actually happens is that if a female is habitual of smoking or alcohol, then this alcohol and smoking at high levels of nicotine can lead to disastrous birth defects, especially because at this third to eighth week, all the major organs are being formed, and an insult at this time can lead to a lifelong disability. The fetus may be born, but may be born with different organal birth defects. Most major organs and organ systems are formed during the third to 8 weeks. The period is of critical for normal development and is therefore called the period of organogenesis or embryogenesis. Stem cell populations are establishing each of the organ primordia, and their interactions are sensitive to insult for genetic and environmental influences. Thus, from third to eighth week, it's time when most gross structural birth defects are induced. Unfortunately, mother may not realize she is pregnant during this critical time, especially during the third and fourth weeks, which are practically vulnerable. Consequently, she may not avoid harmful influences such as cigarette smoking and alcohol. Understanding the main event of organogenesis is important for identifying the time that a particular defect was induced and in turn determining possible causes for the malformation. I think I've explained a bit of this already because it's everything is occurring side by side. If you see at this diagram, now this is again a side-on view of the embryo. This is the neural plate and notochord. Now this is the amniotic cavity, and as this is going to be dividing into formation, will go up and neural tube formation will take place. Similarly, there will be mesoderm will be aligning along this axis, and as this elongates, actually elongation results in folding of the embryo in this direction as pointed out by the arrows. As a result, the fetal position, the embryo position classically we see on ultrasound is achieved. So this is the cephalic region, the head region, and this is the tail region, which is going to be forming the hind limbs and all that, and the buds will appear later on. The endodermal germ layer covers the ventral surface of the embryo and forms the roof of the yolk sac. While development and growth of the brain vesicle. However, the embryonic disc begins to bulge into the amniotic cavity. Lengthening of the neural tube now causes the embryo to curve into the fetal position as head and tail regions folds ventrally. Simultaneously, two lateral body wall folds form and move ventrally close to the ventral body wall. Now, as you can appreciate, now this is curling up of the embryo, which is classically embryo position. Now here, by this time, liver bud has started to appear, and the endoderm is dividing to form the gut later on. While this neural tube has actually formed, and it's this, and Paraxial Mesoderm has started to differentiate in different structures. This is the diagram which is actually showing exactly this is how it all started. This is folding started from here, folds continued to fold along, and this is the time of the lateral plate mesoderm. This is the parietal layer and this is the visceral layer. As it continues to fold, in endoderm actually gives rise to the gut cavity, which is the visceral. As you can appreciate over here, this is the endoderm which is surrounding the gut, and this is the visceral mesoderm which is surrounding, forming the peritoneum and mesentery. While this is how it is surrounding it, while this is the neural tube, this is the amniotic cavity now surrounding whole of the eventually which was the yolk sac. Now this is the neural tube and how these neural cells are migrating. So this is how the folding of the lateral folding of the embryo take place. Summary of the key events. We have to understand that these certain events are occurring day by day. So at day 14 to 15, there is no somite formation and length is just 0.2 mm of the, but this is the time where the appearance of primitives take place. At 16 to 18, notochordal process appears and hematopoietic cells in the yolk cell starts to form. At day 19 to 20, intraembryonic mesoderm spreads under the cranial ectoderm. Primitive streak continues and umbilical vessel and cranial neurofolds begin to form. At day 20 to 21, cranial neurofolds elevate and deep neural groove is established and embryo beginning to bend. Now, all this is going on and on. Actually, it does not occur that first one thing occurs, neurulation will occur, and then the next thing will start. Everything is happening side by side. So, but to make it easier and understandable, we take it up one thing at one time. At 22 to 23 days, fusion of neural fold begins in the cervical region, and cranial and caudal neuropores open widely. Visceral arches 1 and 2 are present, and heart tube begin to fold. At 24 to 25 day, cephalocaudal folding underway, cranial neuropore closes, about to close, and optic vesicle form and optic placard appears. At 26 to 27 day, caudal neuropore closes are closed, upper limb buds appear, and 3 pair of visceral arches are also appearing. At 28 to 30th day, fourth vesical arch is formed, hind limb buds appear, optic vesicles and lens placard appears. At 31 to 35 days, four-limb paddle-shaped nasal pits are formed, embryo tightly C-shaped. It completely becomes a C-shape. At 36 to 42, digital rays in the hand and foot plates, brain vesicle, prominent external auricle forming from the auricular hillocks, and umbilical herniation is initiated. Pigmentation of the retina is visible, digital X-rays, digital rays separating and nipple eyelid formed, maxillary swellings fused with the medial nasal swelling, then upper lips are formed. Prominent umbilical herniation is taking place at day 43 to 49. At around in the last week, on the 8th week, 50 to 56 weeks, limbs become long, bent at the elbows, knees and fingers, toes free, face more human-like, tail disappears, and umbilical herniation persists to the end of the 3rd month. So what have we covered today in this lecture? We have covered neurulation and neural tube defects, formation of neural cells and their derivatives. We have covered the derivatives of ectoderm, endoderm, and mesoderm, and how the actually folding of embryo takes place to achieve the same position. Thank you and keep watching sqadia.com for more informative videos.